Any shop, online store, or company that you've heard of is likely using the cloud. And in fact, Gartner has actually predicted by the end of next year, the worldwide public cloud computing industry will be worth $362 billion. Now, within Azure, we can create, implement, and deploy AI and machine learning solutions independently, and then also baked into our applications. We've been pioneering AI for years, and in fact, ResNet 152, one of the most deepest and effective neural networks for image classification and recognition, is a Microsoft invention, and it came from our research teams in Redmond. Our 3D human pose estimation recently set a state-of-the-art record globally on computer vision research tasks. We were also the first worldwide to reach machine reading comprehension and also human parity way back in 2018. And we have set state-of-the-art records for our vision and speech APIs ever since. Now, if you were following along at Microsoft Build that happened a couple months ago, you'd be very familiar with this diagram that you can see on your screen. This is our Azure AI stack. These are the services that we offer to you to build out your AI solutions. At the very heart of the stack, you can see that we have our Azure Machine Learning Platform. It's essentially, regardless of your experience in machine learning, our Azure Machine Learning Platform is our unified cloud-based environment that you can use to train, deploy, and manage your models. In fact, all of our cognitive services, which you can see on the next tier of that stack there, so our language, vision, decision, speech APIs, all of these deep learning models were actually built within the Azure Machine Learning Platform and using our SDK as well. With cognitive services, we're helping to automate decision-making processes by leveraging deep learning models that have been trained on billions and billions of data points, delivered ready to use through accessible API endpoints. So essentially, we've done the hard yards for you. You don't need to spend additional capital, time, or resources in building out a deep learning model from scratch. With essentially just a single API call, you can automate a business process, deliver unique value, and then also accelerate the decision-making process within your applications, both in cloud and on-premise if you do have sensitive data by using Docker containers deployed on AKS. But essentially, all you need is your data to use our cognitive services APIs. And no matter how much or how little data you have, if you're a developer and you know how to use an API or you want to learn how to use an API, you can do AI in Azure without having any experience as a data scientist or machine learning engineer. That next level of abstraction for our recently rebranded Azure Applied AI services. Each of these services build on the ingenuity of Azure Cognitive Services, and they're built to solve common business use cases that have specific types of data. So for example, you could look to automate the digitization process of physical copies of data with Azure Form Recognizer. You could assist users from different cultural backgrounds to learn a new language with Azure Immersive Reader, or even index a lecture and automatically generate a full transcript of a lesson with Azure Video Analyzer. Overall, together, these three layers of this stack, there is unlimited capability of what can be achieved. And actually, for this year, Gartner's Magic Quadrant has recognized Microsoft as a global leader in AI. So really, there's never been more of a perfect time for organizations and developers and engineers like yourselves to look to Azure and create solutions that push the boundaries of innovation. Prior to Microsoft, I was a machine learning engineer at a Brisbane company and part of a team that worked on computer vision problems for healthcare and then also quantum computing for finance. So I really understand the need for niche solutions to solve challenging problems where multiple stakeholders are involved. I'd like to acknowledge that the problem that you're solving today with AI-enabled marking, that's a really niche use case, and it's an incredible challenge, and it makes it the perfect topic for a hackathon. But that means that there's also a variety of different ways to utilize our Azure AI stack to solve aspects of the problem of automating assessment marking. I've been reflecting on the problem itself, and I wanted to share three immediate focal points that came to my mind at least, namely setting, assessment format and expected response, and then also the level of human-in-the-loop involvement, or rephrased another way, the degree of automation required. So for any students watching out there today, it's imperative to always go from the business problem to the technology rather than the other way around. We always need to understand the perimeter of our problem before engineering upwards. So, given that we have these focal points, I wanted to map these use cases or areas back to the technologies within our Azure AI stack and explore how these technologies can assist in each area. So firstly, let's understand the impact of setting and how that plays a role in determining your solution. So consider how your solution may change if you were looking to automate assessment marking for a large in-person course versus a massive online open course, right? As you could infer, our environment dictates the initial level of automation required. So for example, if we're looking to build out a large solution for an in-person course, we know that there's a high likelihood of physical copies of data through exams and other assessments submitted. To reduce instructor workload in the whole marking process, you could look to automate the digitization process of that assessment piece, which will be physical pieces of data using Azure Form Recognizer or Azure Cognitive Services OCR or optical character recognition. So with Form Recognizer, that's often the perfect place for data that has a structured schema to it, like a multi-choice exam, a lab report, or a tabular document. With Form Recognizer, we're leveraging off computer vision techniques to build an automated data processing software that can identify and extract text, key value pairs, tables, and other structure from our documents. And you can see that on the right-hand portion of the slide there. We're returning bounding boxes where form elements were found with confidence values where, 1 is the highest and then 0 is the lowest in terms of probability. Keep that in mind that this entire output in the JSON document, that was all achieved with a single API call. With the layout API, which is what we're using in Form Recognizer, we're extracting text, tables, selection marks, and structured information from our documents and images using OCR. On this next slide, you can see exactly how that is achieved, specifically with our analyze operation, which is part of our API set. This operation processes our form character by character, word by word, line by line. So essentially, our OCR has scanned through the document on the left and then has recognized the form words, the structure of the table, where the numbers were printed out in the form, and then returns a JSON document, as you can see at the end of that process diagram there. And that will often contain what was written in the form, when it was written, and where it can be found in the document itself. For physical copies of data that don't have a non-structured schema, I should say. So think of something like an essay, a short response, or even mathematical calculations. You could look to digitize that entire process by applying the Read API, which is part of our computer vision API service. So like Form Recognizer, OCR extracts printed and handwritten text, digits, currency symbols from images, and then also multi-page PDFs. The Read API takes, it calls an image and a document as the input in the form of a post request, and then executes asynchronously before returning a JSON document as the response with the analysis and corresponding confidence score. If we had to switch gears a bit and think about assessment format and then a student's expected response and how that would dictate the technologies that could be used and when they could be used as well. So depending on the type of university course, assessment is of course structured a bit differently, both in frequency, difficulty, and then also the format of your assessment and the student's expected response, right? So, for example, if you had a humanities course, something like politics, economics, international relations, it wouldn't be uncommon to have multiple choice essays, multiple choice exams, essays, and then also short response assessment pieces as a key part of the syllabus. On the other hand, if you had STEM courses like mathematics, physics, engineering, chemistry, these are heavy symbol-orientated courses with equation-based problem solving in all of the assessment pieces. In that case, you could actually look to draw inspiration from Microsoft Math. I've included a link in the slide there. It's essentially our application, which uses optical character recognition, OCR, what we just talked about for Form Recognizer and computer vision. We're using that same technology to read a photo of a handwritten symbol-based logic problem, often including maths and chemistry symbols, and it digitizes that equation completely before saving that out to Azure Blob storage for later use. So think about assessment pieces that require short response, for example, or long response or an essay. You could also pivot and look to use our text analytics API, and that would be proven to be quite advantageous, especially since you can implement opinion mining, sentiment analysis, and also key phrase extraction. So, for example, you could look to use key phrase extraction based on n-gram conditional probability algorithms on an economics paper to summarize the topics that were discussed and the overall message of the paper. And from there, you could actually allocate the time that an instructor would need to mark based on the key phrases that were extracted from the student's response. Now, of course, given the clear, differences between courses and the sheer breadth and depth of material covered, I'd be remiss if I didn't acknowledge the inherent limitations that come from a general API's response compared to a custom machine learning model that has been trained on domain-specific assessment data. Now, don't get me wrong, Azure Cognitive Services, all of our APIs, they could fulfill a proof of concept requirements for around 60 to 70% of all use cases. But as you look to deploy and operationalize multiple machine models at scale, you could reach greater success in the automation by building out a custom machine learning model within the Azure Machine Learning platform. So Azure Machine Learning is our cloud-based environment, which you can use to train, deploy, automate, manage, and track your machine learning models. The platform can be used for any type of machine learning, from classical ML to deep learning, supervised, and then also unsupervised as well. But with the platform itself, you can start to train on your local machine and then scale out to the cloud to train your model out on a cluster of virtual machines with multinodal scaling. Within the platform itself, we really try and make machine learning accessible to you. So even if you only heard of machine learning a couple of days ago, or you're a master's student, or you've been an industry veteran for quite a while, you can achieve your machine learning model in Azure quite effectively with the different series of platforms that we offer within the service itself. So for example, if you are new to data science, you could look to implement AutoML or our Azure Machine Learning Designer solutions. So with Azure AutoML, we automate the iterative process of building out machine learning, the machine learning development lifecycle, like parameter tuning, model selection, building out reporting functions for your metrics. All of that has been done for you with AutoML. The scope of the service itself is tightly defined to be a gentle introduction to supervised learning and then automatically selects the algorithms for classification, regression, and time series forecasting models as well. So, for example, course instructors could look to predict semester results using something like lasso regression or classify assessment pieces using key phrases. But essentially, with AutoML, we've done the hard work for you. All you need to do is load your data, select the model type, and specify your exit criteria, like the length of training time or the threshold to hit for a specific metric. But what the service does do is the automated selection of the model itself. So this is obviously achieved by the service spinning up multiple model pipelines in parallel that implements various permutations of algorithms and hyperparameters based on the settings that you initially configure, which is what you can see on the right-hand diagram on your screen there. So essentially, the service iterates through these permutations with different features of your data set and then ranks the results by score for your chosen metric. Essentially, the higher the score, the better the model and is considered to be a good fit for your data. But based on the exit criteria that you can define, the process will stop and then return the range of models ranked in terms of score, which is what you can see on the leaderboard section there. You could also have a look at Azure Machine Learning Designer. It is like AutoML in the sense that it's a low-code, no-code solution with a drag-and-drop UI, but essentially, you can train models all the way from simple linear regression to recommendation engines and also computer vision and deep learning models as well. But essentially, it follows the same code steps that you would in a code-first approach within a notebook or a script, but we've just made that accessible using drag and drop UI blocks, which is what you can see on the diagram there. Whilst you need a basic familiarity of the underlying methodology of machine learning to correctly connect the modules together, you don't need to code any of the steps. There is the option where you can actually fill in the code that represents each UI block, but that's not necessary to actually deploy a model. Designer gives you that flexibility in the granular components of machine learning, which AutoML doesn't. So, for example, you get to tune hyperparameters, you have input into model selection, and you also get to choose the metrics for evaluation. Or, for example, if you wanted to execute k-fold cross-validation. When it comes to deployment time, Designer helps you automatically convert the training pipeline into a real-time or batch inference pipeline, all done with a single click of the button. You don't need to do anything else. But from there, you're able to publish your pipelines to a REST API endpoint and then submit a new pipeline that runs with different parameters and datasets. Now, of course, if you are coming from an engineering background, you could look to build your models using our Python scripts, like you would code from a VM or in a Jupyter notebook. The beauty of the Azure Machine Learning platform is that it's a managed governance platform for machine learning. I've coded straight from a VM before. It becomes very easy to lose track of your progress and then also not bake in effective risk management and governance procedures within your model building process. With Azure Machine Learning, you can manage your models, endpoints, compute, deployment infrastructure, all within a central place. You don't need to have an external third-party tools to monitor your model's metrics, logs, or an additional solution to put into place to actually test out your model API endpoint. It's actually here that's the capability of the Azure Machine Learning platform where you get to create your domain-centric models trained on specific course data to help automate assessment marking. So, for example, you could look to implement latent semantic analysis and distributional semantics to determine the context of an essay or a lab report, and then use the probability scores that are returned from the model to run an NLP text classifier on top of that to assign a certain grade or allotted feedback bucket. Another example could even be satire detection for English literature or journalism essays. Essentially, you could even change how marking is done altogether by creating a machine reading comprehension application and then query a student's assessment based on key criteria and points from a criteria sheet and have the AI return a summary of what a student wrote in their essay. All of that is possible with machine learning, and you can host that within the platform itself. In fact, you could draw inspiration from Microsoft's ResonNet, which you can see the architecture on the right-hand side of your screen there. That is how the model has been built. But essentially, we created this neural network for exactly that same purpose, for machine reading comprehension. And from there, you can mimic the inference process of human readers by drawing inspiration from computer vision techniques and then also reinforcement learning. So essentially, ResonNet, it scans a document, it focuses on different parts of the text until it's able to learn context. And from there, you could ask a domain-centric question to the assessment piece and get the AI to answer the question with the best context and inference from what the student wrote. So essentially, my point is, regardless of what deep learning NLP model you want to build or you want to create machine reading comprehension that revolutionizes how marking is done, my point is you can solve different aspects of the problem within the Azure Machine Learning platform, which is often your best bet to create seamless managed governance models and then also deploy out to Azure DevOps, because we always have to think about production and business value at the end of the day. Now, part of recognizing a machine learning opportunity is recognizing the opportunity to deploy your model into production, where it's actually acting on real-world imperfect data. Part of operationalizing your model into will be ML ops or machine learning operations, in case you hadn't heard of that. And that borrows concepts from DevOps practices. So as we head into an era where custom machine learning model is going to become quite common, we know that the leaders in the field will be the ones that can scale their machine learning solutions rapidly and then also deploy to meet business needs. With the integrations between Azure DevOps and the Azure Machine Learning platform, we can create CI/CD pipelines and implement continuous delivery and continuous testing. We also get to experiment and deploy models more quickly and refine quality assurance. We get to collaborate, build, test, release, and monitor as you create reproducible models and reusable training pipelines, and implement quality control, which is so key and is part of risk management best practices. And quite honestly, I don't think we see that enough in industry itself. But then also A/B testing as well as an automatic retraining process. So all of that is capable because of the Azure Machine Learning platform, where you get to bake in and build your custom models from scratch and then integrate outwards into Azure DevOps, which we often actually have automated a lot of the process. There's a great repo. It's called the MLOps Python template. We've done all of the hard work for you. We've written the YAML code for you. All you need to change is around 3 or 4 variables and then 9 files with your own custom model. And from there, you can automatically deploy and automatically retrain your model as it goes out to production. But I guess regardless of the setting or assessment format or expected response, being able to search over digitized pieces of assessment efficiently, all whilst calling something like text analytics or OCR, all of that is really crucial. And you can achieve that with Azure Cognitive Search. So here we implement something called knowledge mining on our data, and we can create a central knowledge repository of our digitized assessment, all whilst calling the same AI and machine learning models that you already just built, all the custom ones on your central domain. You can call that within the central Azure Cognitive Search platform itself. And that can help you search over a student's assessment by course, by faculty, by department. So with Cognitive Search, we're actually provisioning the bare bones of our own customizable search engine. And that's an incredible thing to think about, especially when you realize that there aren't any restrictions on the data source type. So at a high level, we ingest our data, a digitized assessment from our massive online open course or in-person course, and we save it within SharePoint, blob storage, or Cosmos DB, for example. In that next process of extraction, we're then pushing our data to something called an index, and that helps us map the input fields of our data to the output fields. So essentially how we take our data and make it searchable. We have control on how we create that, but once we are happy with it, we can then define something called an indexer. An indexer is a crawler, and what that means is that it's going through your data line by line to extract searchable text and metadata to populate your index. So keep this in mind, this is all done with pretty much a single click of a button without any code for you to write either. Our indexes also drive the AI enrichment capabilities of cognitive search. So essentially, it takes our skill set, it calls an API like text analytics, like OCR, like form recognizer, and then implements that on our data. So think of it almost like a magnified lens that goes through your data again, but now with the capabilities of AI and machine learning as its superpower. But once that whole indexer process has been done, our document is considered to be cracked. And then from there, we're able to make queries. And that's typically done through Portal or using Postman for REST API. I also wanted to spend some more time on how cognitive search really works because it's a fascinating service and it also makes AI a lot more easier. From this diagram, when we actually create a search service, we essentially have the service sitting between external data sources and then also our application that we're building. There are 2 main brains to the cognitive search experience, which is our indexing engine and then our querying engine as well. With indexing, we're taking our data, we're loading it into the search service to make it searchable. When we start to consider the AI capabilities of it, that informs the indexing process of using something like a custom skill template. The querying engine, on the other hand, that runs once the index is populated with searchable text. So, for example, if we enter in a search for a particular student's name or course, our client application will send the request back to the querying engine, which breaks it down and assigns a score to a matching document. Typically, our search results will always return the URI of a request, and then from there, our application will handle the response and return a JSON document that actually contains all of the relevant documents that we found and ranked in order of relevance and number of matches. Think of Azure Cognitive Search as the adhesive glue that unifies our Azure AI stack. We can create a central knowledge repository of assessment pieces, for example, within a single API call, you can implement something like topic detection, machine reading comprehension, satire detection, and any custom natural language classifier that you build to automate the initial stages of assessment marking for long response and essay assessments. Now, finally, I'd be remiss if I didn't talk about this, but we should always consider the various levels of human in the loop feedback, depending on the above factors that we just talked about. So, depending on the course setting or assessment format and expected student response, the level of human in the loop feedback is going to change respectively. As in-depth as our AI technologies are, we should always be really mindful of the degree of automation that we're aiming to implement and the consequences of that choice. Andrew Ng, you may have heard of him, arguably one of the fathers of modern-day machine learning, refers to AI as a spectrum of automation, and you can see that diagram at the top of your screen there. From human only all the way out to full automation, where there's no humans assisting, it's just the AI running and doing and executing its model. And whilst that seems commonplace to us, it's important to consider the limitations of AI will always be dictated by the quality, quantity, and exposure of our dataset. Whilst we can always automate the main aspects of something like assessment marking and reduce the overall effort demanded from an instructor, we will always still require human knowledge as SMEs to interpret the probabilities of something like topic detection or citation intention. For example, although we could fully automate the marking process of multi-choice assessments in the same way that you could just implement a binary or multi-class classifier, the route taken to answer a focus question for an essay, for a thesis, or even the problem-solving approach taken in physics or math, that's going to differ student to student. So having a human in the loop is inherently required to provide a human perspective of AI and assurance. However, you can reduce the level of involvement of a human in the loop by utilizing something like a gated feedback response framework that will be dependent on the probability scores returned by our models, which will give an instructor the flexibility in determining how they allocate timing in their marking or a tiered feedback response. And I've tried to articulate that in the bottom diagram of your slide there. So, for example, if we built a topic detection model in Azure Machine Learning to summarize and classify law essays, we'd be able to reduce the initial workload for an instructor by auto-sorting the exams into buckets based on the probability score returned. So naturally, exams with the highest score for detected topics can be perused by an instructor with a default feedback response that could then be customized to each student's assessment, whilst exams with lower scores for detected topics would require a human SME to mark, or at least a tiered response of how much time they spend. How a gated feedback loop and response framework is created and implemented is going to be dependent on engineers like you, collaborating with course instructors, academic deans, students, and then other important stakeholders in the pipeline as well. You notice that I actually said students as a key stakeholder in this automation project, and it's because they are. They are the beneficiaries of automated enabled marking processes aside from lecturers and instructors. It's only ethical to really involve them in the design process and in the feedback loop to confirm whether the AI has interpreted their assessment correctly. This could also feed back into the algorithm itself as a reward for it to learn whether or not the inference was correct using something like reinforcement learning, right? But essentially, ways that you could implement that is pretty much unbounded. But the most common ones that you could look to use is Azure Bot Service, built into Microsoft Teams or into a course site to automatically route any questions, comments, feedback to the automated marking back to tutors and instructors. Lewis, our language understanding intelligence service, that could be integrated into our bot as well. Lewis is our custom machine learning intelligence service that applies natural language processing to a user's conversational natural language in order to predict the overall meaning and pull out relevant and detailed information. So, for example, in our use case, you could keep the gated feedback framework, but then include services like Azure Bot Service and Lewis to reduce the intensity of repetitive questions that are asked about feedback and marking to an instructor. Now, of course, in the setting of your hackathon, it's unrealistic to set the target of building out an application that's going to cater for different settings, assessment formats, expected responses, and then also have a gated human in the loop engagement levels. I definitely understand. I would suggest focusing on a particular course or a gap in the solution that you can see and prioritize the use cases where the gap to human level performance is the largest and spend your energy in building models and processes there. However, as you do consider to scale out your solution over time and integrate outwards post hackathon, it's important for us to always optimize our solution design and consider how it's going to best generalize or create multiple model endpoints that could be called simultaneously within a multi-tenancy environment. So to recap, we're focused on these main focal areas of automating assessment marking, namely setting assessment format and expected response, and then finally the degree of automation or the level of human in the loop involvement. Within each of these points, we explored relevant Azure AI technologies from our stack and then also showcased how they could be used to reduce inefficiencies in assessment marking. But as you build out your solution within the hackathon and then post hackathon, just know that the Azure AI stack, it's going to cater for your skill level, your exposure, and whatever use case you select within this context. And all you really need to add is your imagination and creativity to solve the process. Thank you.